Good afternoon, general readers. It's about September 21, 2024. And this afternoon, in Moment in Motion, will be a continuation of the ongoing dialogue, if it's a monologue, a dialogue, a discourse in the study of the theories, of the principles of the scientific method as applied to mechanics, as with regards to that there's quite a backstory to it. And what we have today is, in a sense, a combined and refined, yet partial and incomplete, overall elementary account of moment in motion. Here today, then, the subject is momentum. So in these talks, a lot of the approach has been this thorough kind of sum of history, sum of potentials approach. So the potential fields are the real fields. And with regards to conservation of energy, then, in any kind of mechanical setup, ansatz problem, that there is that the energy is conserved, and so whatever is represented as kinetic energy is also represented as it's in negative amounts, the potential energy. So that just helps to kind of reflect that when I talk about momentum and conflate it with inertia and energy, it's that inertia is kind of the more real quantity considered here, because it's from the perspective, the side of that the potential fields are the real fields. And so this will just help to explain that when there's consideration of m mass times v velocity, whether that's inertia, as it is for when it's zero, or momentum, that it is the definition of momentum today, since a few hundred years ago, but not constantly since 2,000 years ago. And the overall consideration of this vis-viva, which is this alternative kind of notion, is about the surrounds and the circular and the round of it, and vis-motrix, then also is with regards to a lot of these other considerations of the discourse that are in effect still representing open questions. So in this manner, then, with regards to kinetic energy and potential energy, and that the kinetic energy is just kind of like the last linear impulse of the potential fields. This is all one real field of forces. Their field theory is a theory of forces, and it's a vector field of sorts, and that's the formalism. And it's as of it's not the classical perspective, which is basically the classical perspective is one point of view of one observer and a fixed observer. So herein is with regards to these notions, including overall concepts as of the premier theories of the day, and the study of the evolution of Einstein's theories, for example, and their considerations with regard to mechanics, and Einstein's goal, his search, his research for a total field theory where there's revised the laws of mechanics, and here that those are considered the kind of these Newton's or the zeroth laws of mechanics, that thusly what's being turned over then is that from the perspective of the view of this discourse, it's not necessarily the same story as the standard linear curriculum, yet it's still perforce relevant and critical, that it establishes much the same results than for what otherwise are these extended results. So today, what that gets into are things like this. Much like the potential is present in any of the considerations of the balance of the energy, because there's the conservation of energy, which is deemed a conserved quantity and thus invariant and must always balance out. And then there's the conservation of momentum. And momentum is kind of given that it's as of this simpler system, and so it well as sensible, fungible, and tractable, it's not complete. And what ends up happening is that there's all sorts of these assortments from any given perspective other perspectives, of the forces that result called fictitious, or kind of in the model of the particle wave duality, that are hidden variables or supplementary variables that are still causal, they're still explanatory, and they're still as of in the balance of things, which one ends up being relevant as with regards to which is zero and which is non-zero. So the way to consider that here is that with regards to meters per second or seconds per meter, what's in effect is greater than 1. So either it's reciprocal, maybe it's as of a constant if it's in a state of constancy, or it diminishes or vanishes, or grows or exchanges. That it just goes to show that what's in the notion of fictitious from one point of view, in terms of the dynamics of the system, when it turns around, can be the classical again. And then what was classical and the center of it is instead turned back around over, and that becomes fictitious. Only fictitious, not in the sense of anything that it's of its unreality at all, but only fictitious in the sense that in the model that it can't be ascribed the same primariness in the elementary account. We have a theory, we have definitions, often axioms. These are the elements of the theory. And then as with regards to the interplay of all these things with momentum and inertia, that over thousands of years, it's been turned over several times, that inertia is resistance to change in motion, and momentum has the same definition. And then as with regards to that, inertia doesn't really enter the story. And then in terms of like relativity, and yet as with regards to that, well, that's still all in one frame. Like we all live in the terrestrial frame, for example, with regards to the total. And this is a lot addressed in the considerations of Einstein's Out of My Later Years, a great parting gift from an eminent theoretician and a physicist and a philosopher in physics. That that's just kind of help establish why that talking about mass times velocity and it's linear has that reflects both momentum and inertia. So then as well as with regards to the vis-viva and vis-motrix, it's kind of like Leibniz says, hey, anything that starts to revolve is going to let out this other factor, m squared over v squared, or mv squared, vis-a-vis mv. So what it starts kind of looking like is that in the theory of the ordinary differential equations and the Galilean and the linear and this kind of stuff, that as well, that's an extraordinary itself. That in the whole terms where it's simple and linear, it's fractional or transcendental terms in terms of the wider system. So this is quite an ongoing thing that's been ongoing since thousands of years ago, and recently in terms of like since a few hundred years since it was given that for after Galileo and some of the various things that go into whether he disclosed things to science or withheld or reserved things later that are actually relevant, has that these definitions aren't fluid anymore by any means. This is our standard linear curriculum, yet there is this wider, fuller, extraordinary, non-standard, extra standard, super standard to make out this super classical, because it results that in all these manners of the empirical of systems as they get more and more complex, that aren't just the classical cases of like the two-body problem, but getting into a world where things are like, we can't just consider things as of a cloud, but they're all as the orbits and these kinds of things. That the sum of histories, sum of potentials is what principles arrive at the theory must be, and that it's also universal and not just of a limited view, that these matters of perspective and projection and the relevance of geometry and the continuous manifold that's Euclidean everywhere, yet as well involves in its reticulation all the continuous manifold, the manifold that is still yet continuous, and that there's everywhere geometry. And as with regards to these matters of perspective and projection, as a relevant abstraction from geometry, and as with regards to the observer, and all these sorts of setups, experiments, and ansatz, and the thought experiments, the Gedanke, that result why then the definition arrives as so follow. So, trying to think that over, because momentum is controversial in that sense. And as with regards to pseudo-momentum, which is as with regards to dynamics and action. And for example, the empirical and that it's in the empirical and tribological things are just measured after their design as trial and error, vis-a-vis being all theoretical. It's foundation, the dynamometer, and these kinds of things. And as with regards to moments of inertia, which is otherwise let out as undefined, yet just reflects the centroid and the central tendencies of some things, and the uniform tendencies of some other things, and the polar tendencies of some other things, that it arrives at then a little bit more just kind of didactic account of why it's considered both adherent to our common body of definition, because there's no change in things, while it's still fuller and more conclusive in the comprehensive, as where the otherwise these more simple elementary accounts, which are easier, more sensible, more fungible, more tractable in their limited milieus, yet have their classical solutions. So then what we're looking at in 4 is more classical, paleo-classical solutions, as with regards to like Zeno's graduation course and the doubling spaces and doubling measures. And yet as well, just as with regards to something like the law of large numbers and classical probabilities in a world where statistics is primarily governed by Bayes' rule of classical priors, the prior probabilities, and conditional expectations which so follow, that is particularly as an account of Bayes' rule as fundamentally discrete and not continuous. And so, as according to counting arguments, why it works great for such manners of counting arguments of the discrete, yet with regards to the fuller analysis that there are more laws of large numbers. And besides expectations and our estimators from our theory of probability, and it's a scientific statistics and a statistical science, that there are these other laws of large numbers involved in the continuous and the infinite. That 0 meters per second is infinity seconds per meter, and 1 meters per second is 1 second per meter. Then is coming around, that just kind of helps explain some of the other aspects of the background of why the classical linear approach is what it is. And then the usual approach of the Laplacians and the sum of partials, or as with regards to things like Hooke's law and the finite well versus the infinite well of potential, and with regards to other applications of numerical methods in physics, and you can consider something like the linearization of the small angle approximation, which is so in the limit, and as to where that is yet admitting as of a term of a numerical method. It's error after the approximation. So these are the kinds of things that live in the theory today, Hooke's law and the linearizations of these kinds of sorts that go into formalizing things like the convergence of the Fourier series, which is a fact given and a derivation given. That here it's also been explored and explained some of the reasons why. What are some of these being uniqueness results are instead distinctness results because there's a wider milieu. And so it does kind of make it so that with regards to these sorts improvements, perceived improvements to the theory, that it has these features equipped for the numbers of concepts of more than one law of large numbers, concepts of more than one definition of continuity, concepts of more than one definition of the spaces of zeros and ones or Cantor spaces. That thusly it arrives at the more replete. After what's complete, the regular, the rulio, according to induction complete, that it's established that there are some things that induction cannot complete, yet still are so. The deductive closures, and as with regards to the inductive impasse, and with regards to the analytical bridges, and then mostly for these three definitions of continuity at least start to give underneath for their elementary count together of continuity as elementary, and that this goes a long ways towards simplifying greatly things would otherwise still have to be assembled much later in the theory with the almost everywhere bits, or the Jordan measure and the Dirichlet function and the Dirichlet problem after harmonic analysis, that being these days called the potential theory, but linear and linear and linear again, as it were. That hopefully then that helps convey the intended account, that after a deconstructive elementary count, and it's discussed in many of these issues here, or in lots of these discussions as well, since 2,000 years, this paleo-classical approach to the supraclassical, that these days then there's also, of course, the benefit of there existing all the data and the ability to contrive many sorts, simple tabletop or readily fabricable mechanical experiments to help show that such matters of the nutation of a top or something like that have these overall surrounds, which can then thusly have improved the consideration that there exist solutions at all, like that orbits are easier to figure out than collisions or something like that, then that they don't, because otherwise they don't, and then that would be insufficient for having a candidate in foundations. It's a practical working theory, limited to its realm, where here the idea is the object of the elements of Hilbert's entire infinite living working museum of mathematics. So where we left off yesterday or last time was reading from the Dictionary of the History of Science. So in Heilbronn's section on mechanics, we'll pick up here where we left off. I had a chance sometimes to review some of these videos once or twice, a week. I'll listen to some of them or some part of one of them. And so, reading from this space sciences book and the planetary electrostatics and electrodynamics was really enlightening, because a lot of these are very underexplored concepts and known things popularly, and so a lot of people when you consider kind of the popular crowd, the mob of people who have interest in science and want to know a consistent theory for it to satisfy their requirements and desiderata of aspects of knowledge, that a lot of these things are well specialized, yet as well in parts of very thorough and holistic accounts, that help explain that there are a lot more factors going on in the bigger theories, with their grains of truth, as it were, that then kind of balloon to have to explain everything. There are these other factors and aspects in the planetary and the terrestrial here that deserve at least as much attention in regards to any of their changes as various other metrics. So, in Heilbronn's entry in the Dictionary of Science, we got up to talking about the dialogo from Galileo. In free fall, velocity v and distance s are respectively gt and gt squared over 2. Combined geometrically with a consequence of Galileo's impetus theory. So the impetus is like the propensity, and impetus is also otherwise more of a classical notion of force, something that's given force. Now here, it's very familiar in the theory that everybody knows that there's mass as the quantity, and it's conserved as of in the milieu of the exchange of energy up to complete mass energy equivalency. That then there's weight, and so weight is according to being in the field or as being accelerated. So that's kind of split off into two ideas. It's like that there's weight in the well of a much larger body, like the terrestrial, the Earth. And there are g-forces, which kind of say, well, if given the equivalence principle, that acceleration of gravity is the same as acceleration as of the reaction mass or propellant, most usually, but otherwise is via any means of impetus, the force, has that the equivalence principle is let out, so that there is a modern accoutrement of big science experiments like Lenz, Thüring, and Parker that help at least bring back some of what's going on, and that for example Einstein had to kind of pave over to pave together his two theories, general relativity, which is first, and then special relativity is his theory of relativity. So that said, then here with regards to this theory, without resistance, a violent motion will persist with constant velocity. It's kind of like our laws of rest, and motion. So with regards to that, is that it generally everything is considered to be in its own frame. There are no privileged frames, is the idea in at least one perspective of the theory. And so that then thusly there's only velocity, there's not really rest, because and this is like Born's restless universe and things like this with regards to anything ever having a velocity of 0, because with regards to what is the question, as with regards to setting a clock to setting a clock to setting a clock, or to measuring a stick to measuring a stick to measuring a stick. They can agree, and then as with regards to whether one or the other is as of the privileged, as it were, has that still in the total theory there is kind of a clock hypothesis and the wider frame and all these kinds of things. Just helping explain that rest and motion, that what stays at rest, and what stays in motion, are still two different things, because they are related to all their surrounds, and besides their classical energy that they have, they live in the world of all the potential energy that is the sum of potentials. So they just goes to show that it's kind of like meters per second or seconds per meter, whether it's rest or motion, or vice versa. Parabolic trajectories for projectiles. That was discussed here quite a bit about as with regards to the vis-viva, as it's considered, or active force. And this idea that contributing to the Magnus effect, which in some sense has an aerodynamic and fluid dynamic explanation, that the other empirically evident still existing components of that and the ones that they don't have any hydrodynamic or aerodynamic effects at all, yet still last longer. This is considered this aspect after mass and weight and heft. So heft is the idea that the heft of something is like the weight of something, and it's usually, that's just kind of its natural definition of as in accordance to weight, or to heft something is to kind of measure its weight, and that here heft also indicates kind of where it's a contribution to resistance to change without really having mass, except it's equivalent to the mass, equivalent to the energy, without really having weight so much, because it was kind of given heft. And part of this exchange of the open system here is momentum is underdefined. Still has, then it has the same inertia, kind of, as with regards to that being part of the surrounds, so that it's considered here that that's part of the definition that is introduced here as among the terms, which include the walk integral after the stop derivative, and this pause integral and run derivative, which the idea is being is like add up these pieces that have their dynamics, which result whether or not they're either central in the system or coming and going from being fictitious in the setting of the other potential forces, all being together potential forces. That's this hop, skip, and a jump, the snap, crackle, pop, jerk, jink, and jank, or jounce, and as with regards to the acceleration and deceleration, abceleration, and with regards to these notions here of the punctuated motion, as with regards to that helping to explain differences in perspective according to meters per second or seconds per meter, or the inversion of units, what happens when systems arrive from one to another in the dynamics overall. So this is then usual enough, and of course attached to all the theory and definition that there is, and the discussion and the discourses. So Galileo's revolutionary concern with ideal real motions became the theme of progressive 17th century mechanics. Descartes, 1596-1650, among others, insisted on the principles of relativity of motion and of rectilinear inertia, and many corpuscular philosophers sought laws of collision to describe the encounters of billiard balls. So on the one hand, the collisions of billiard balls are most ideal, but on the other hand, they erase two different notions of ideal for them to be so simple and less contrived. So kind of like there's a concept that then in the model of things like atoms in a gas, or the constituent elements of a gas, these Hookean barbells or dumbbells as they are, that they have, that they're these levers besides being billiard balls everywhere. So there's these two things at once. So it's something to be considered that the rectilinear is sure and is geometric and it's classical, and the billiard balls offer one of the most excellent experimental settings because they're uniform, and thusly they don't enter into any of the dynamics among various dimensions. These various dimensions. So let's get on with this here. It says Descartes provided too many such laws and placed them at the head of his Principia Philosophiae. So we had already read this section a little bit before, and what it goes on to reflect is that these are the empirical aspects of it. And so if you've ever played billiards, you're familiar probably with the concepts of masse and with spin, and also with regards to striking the bumpers and their phase echoing on it, hearkening back to the discussion of the waveguide and the waves as with regards to channels of waves. and with regards to the incidence of reflection and the phase, and how that basically, that the ball rolls as it bounces. And so as it's rolling, as it bounces, the otherwise exact geometric collision starts at nothing, goes to kind of where it results, that then finally, when it leaves that and they no longer share an interface together, that then it flies off in its course while still rolling and spinning and sliding on the table. Going to show that these effects, as of, for example, linear waves that are geometric, and as well their optical character in the phase, and what results, that these reflections are according to the angles reflections, and as according to the incidence, the reflection, anything that's not a straight on, dead on hit and bounce right back has these dynamics involved. They're formally non-zero. They're negligible largely, and when you consider even a ball and another ball, or a ball and a rack of balls, these all have to add up, and they're formally non-zero and non-negligible, and almost all effects of good shots are according to practically the application of striking the object ball and resulting these actions. Descartes, mentioned by Christopher Wren, John Wallis. So John Wallis is a lot famous for the lemniscate, but then he's also very much famous for that it's basically from Wallis that the modern definitions arrive of momentum and the kinetic and inertia as left alone. So Wallis is a great figure in that. And Huygens, so Huygens we talk about here with regards to Huygens' principle is that waves make waves. Waves radiate and make other waves, vis-a-vis any other aspects of these considerations here, the geometric and the optical, which are as of rays. So waves and rays. Rays being geometric lines, and waves being expanding circularly. Or as with regard to the oscillations. I found a great book online the other day. It's Nayfeh's Nonlinear Oscillations. That is a really good survey, and it also has a lot of descriptive character in it. And so among works of that sort, that's so far the most thorough that I've found. It was Nonlinear Oscillations. The postulate of composition of velocities. So this is, in regards to earlier discussed, the great utility of addition formula is addition of velocities, because that is about the easiest thing to do. When you have velocities as a tuple of numbers or a vector of numbers, when you have vectors as a tuple of numbers and vectors as a vector of numbers, then you can just add them up component-wise and they add up. That's great, and it reflects the addition of this linear and geometric as accords with, for example, perfect incident reflection and this kind of thing, which is just noted is ideal, yet this wider ideal is that it's just partial. So. Postulate of composition of velocities used implicitly by Galileo in his derivation of ballistic trajectories was made explicit by Verignon and Lamy. So we talked about these before. Principle of conservation of a vector, most of these. Newton, synthetic work, capping the tradition begun by Galileo. Although Newton concerned himself with the nature of body and force, he tried, not always successfully, to give his results in the Principia, in terms of velocities, accelerations, and other ideal real observables. Observables resulted as of for tools, so it's as well and plainly observable that these effects, for example, of the wave mechanics in the sonar, as just mentioned, or the billiard ball mechanics as with regards to the non-ideal are as yet ideal. They're as yet observable and measurable. Uh, we, these days, for example, you can imagine inverse kinematics or motion capture, for example, as a little bit wider realm of observables than beginning and ending, or as of one clock and precision of timekeeping. So it's certainly so that this is discussing a well-advised, proper account of observables, yet as well that there are more. So, the Principia established the basis for the theory of motion of mass points. So are points ideal? Well, they're theoretical. And set the problem, showed in the case, gravitating spheres and spheroids, macroscopic effects, largely courtesy Kepler. And here we get into talking about the idea of the vortices. So both Descartes and Kelvin have these nascent theories of the vortex, or the vortices. So this is basically the idea of a spiral. So just like the billiard ball is considered as moving linearly, that as well it's always spinning and it's always sliding and it's always, in a sense, following a spiral course. So the vortex is the idea that as a complement to anything that's linear, that is, well, there's the entire rest of it as represented by this packet, as it were, of forces, the vortex. And so it's a very general thing to apply to anything, as with regards to the sum of all the potentials in and out at any one time. In fact, arbitrarily, abstractly, there are all sorts of the continuum of these things at any one time. And that from moment to moment, half of them disappear with regards to the other half overall. Neither really interacting in regards to the interaction of terms, yet formally it's always so that whether zero or non-zero, the surrounds exist. So when it discusses how Newton tore down Descartes' theory of vortices as just not measurable or not observable, it doesn't dismiss it from otherwise the consideration of the surrounds. And so for Descartes' theory of vortices or Kelvin's theories of vortices and many other thinkers, and these days we can get up even to stuff like gravitational singularities inside the Schwarzschild radius, according to the laws derived by Chandrasekhar, gravity and mass density would result a black hole, from which, thusly, according to this model of forces, that it will always be constituent and only ever grow. Well, there's also an idea is like that all of space-time is considered like a virtual opposite of that. And it's just like things go out from it. White holes everywhere. And so when you hear about in the theory the black holes and white holes, they're complements on the quite total scale. Yet as well to reflect that for the gravity in the middle has stuff to do with density, mass, and the force of gravity, then you have at least these three complementary notions of the white holes. The black hole's own virtual particle, the universe at large, and the C. This is the Dirac positronic C, Einstein white hole C. So this goes into some of these reasons why Descartes' theory of vortices is set back on the shelf in the display next to lines in the Galilean, because that's where it is. And they always go together, formally, abstractly, if not according to the precision of our meter sticks and clocks, practically. In the wider milieu, in the sense of dynamics, they do have practical import. So that's really the consideration here, is that mathematics doesn't have infinitely many higher orders of acceleration, and it needs one because 0 meters per second is infinity seconds per meter. Descartes, theory of vortices. This is the subtle matter. It gave an approximation to a quantitative theory of motion in resisting media. This is these days about diffraction and refringence after reflection and refraction in the theory of waves. These waves. There's also the elastic and inelastic, and as with regards to collisions, and the point impulse not being a line, yet instead being a curve. So it's curvilinear as well as rectilinear, whereas it's still so much simpler to keep things computed with vector addition and otherwise these things. So that helps to explain that this is part of the approach to have a simpler way to cover this entire dialogue and background, which according to historians of science is worth keeping because otherwise it would not even be mentionable. The 18th century systematized and extended Newton's approach and synthesized it with the mathematical methods of Leibniz and Johann Bernoulli. Generalized the principle of virtual velocities into the anchor of statics. So it'd be interesting to study Bernoulli, of the Bernoullis, into the anchor of statics. Leonard Euler subjected the dynamics of mass points to analysis in his Mechanica. Bernoulli, Clairaut, and Jean Laurent d'Alembert devised the fundamental equations for the flow of inviscid fluids. In our fluid models, there are quite different aspects. Kind of like this, the if the black hole has gravity, density, and mass, and then inviscid fluids are as with regards to viscosity and the capillary action or surface tension according to the fluid nature of a thing. Electricity and liquids are totally different. They on the edges or in the core they are opposite, infinitely many, this way to each other, inverse. So it just goes to show that while it is so that helps a lot for starting to get from the inelastic to the elastic, something like the collisions, and the adiabatic and the non-adiabatic and so on, that Euler helped find a line and help find a principal branch and help establish a distinctness result, and that sometimes is too quickly considered a uniqueness result when it's formally not. So it's a part of the thing here. Euler, through such concepts as moment of inertia and an instantaneous axis of rotation. So these are the laws today. These are theory. He made the theory of the motion of rigid bodies, which is ideal. Theoria motus corporum solidorum. Another systemization occurred through synthesizing principles apparently opposed. So that's kind of also the idea here, is that some principles that apparently singular are comprised of opposing principles. These are the unstated assumptions. After a long dispute between partisans of Leibniz and Newton, this is the vis-viva and vis-motrix argument, agreement was reached about 1740 on the proper mesures, plural, of the force of moving bodies. Momentum and vis-viva were recognized as different integrals of the second axiom of motion. The property of Leibniz's principle, the conservation of vis-viva, acknowledged for elastic collisions. So this just helps go to show that in a lot of things, it's like it's not going to be simpler to have started from these simpler principles and then wider surrounds. The grand synthesis of 18th century analytical mechanics is Lagrange's mécanique analytique, starting from the principle of virtual velocities, already refashioned to apply to dynamics by imagining a moving system to be at rest under suitable impressed forces, D'Alembert's principle. Lagrange set forth general mechanics and hydrodynamics as a matter of pure analysis. Now, I introduced the word he says here of pure analysis, but it's applied. So the pure mathematics, the applied mathematics are pretty much always both. So the idea is then, with regards to anything that's, these issues of the singularities and the multiplicity theory, have these various opposite accounts or the unstated accounts requiring this thorough elementary deconstructive account to arrive at ways to put it back together, especially when the foundation of mathematics is equipped with any new thing, because then all this stuff is only after it's like we're dealing with an Archimedean field here. There was not in the toolkit the non-Archimedean spanner, which here may be a thing. So, the principle of D'Alembert, though, I'll look at that some more. D'Alembert seems quite central. And it was also involved with the integral equations, and the consideration here that the identity dimension is actually an envelope and not an asymptote of the linear fractional equation, Clairaut's equation, and D'Alembert's equations. After a long dispute, vis-viva, mécanique analytique, D'Alembert's principle, Lagrange, where the Lagrangian these days is like, according to time, this dynamical system is what it comes out of it. So usually it's kind of attached to something like after a Hamiltonian, which is a way to solve classical linear systems, and the Lagrangian is kind of after that, and it is what it is. Set forth general mechanics and hydrodynamics. He worked not directly with force, but with its integral over space potential. So this is a great concept to help explain that the sum-of-histories is this concern, and that's why we have today the conservation of energy is still a thing, and the conservation of momentum is let out as kind of like what's lost in the dynamics by the time it all spins around and comes back out. It's integral over space potential, which breaks the immediate connection between motion and its causes expressed in Newton's second axiom. He boasted that he needed no diagrams, no appeal to geometrical intuition to set up and solve mechanical problems. Lagrange needed only the Lagrangian, the difference between the kinetic and potential energies, and the calculus already developed into a supple analytical tool by the perfecters of dynamics. One of Lagrange's notable results was to incorporate a generalization of Maupertuis' principle of least action, extremum principles, into a system. So the least action is the sum of histories, and the sum of potentials indicates, according to a continuous manifold, this gradient, that along with least action there's a gradient, and so this time, it's a ray of time, and it always goes forward. So it's always minimizing the distance between it and the next instant, the forward passage of time. In 1744, Maupertuis had replaced Fermat's principle with a similar law that required light to travel more quickly in optically denser media. In 1747, he applied this proposition that all material processes occur in such a way total action created is a minimum to collisions. Here it says, with regards to trying to figure out that for the orbits, that the energy is still conserved in a sense. The action of a system of particles is the sum of the momentum and position, product of the momentum and the position. So this is where Maupertuis' introduction of that being the action has here, it's instead to be figured out as like, well, what you got there could also be read off as inertia, and least action as no action. So this gets into why it's a great thing to have kind of the survey of the development of the ideas and the derivations and the development, because then it helps to be able to afford as part of a deconstructive account of the surrounds of the mathematics and this foundations. The goal is to be able to replay it and revisit these derivations of these great touchstones with which everybody else who knows the canon will be familiar, to be able to put them together this way. Euler showed that in the case of motion under a central force, the integral of the quantity p dq is an extremum, not necessarily a minimum. Lagrange made delta integral p dq equals 0, general, and freed it from the error of final causation with which Maupertuis had encumbered it. Well, he's picked a branch. A true minimal, as exposed to extremal principle, was formulated by Gauss in 1829. Principle of least constraint. We have dynamics in our mechanics about the space frame and frame space after space contraction, and it's real, so that helps to affect to reflect that rotational bodies in the kinematics, the dynamics of the kinematics, have that they're not necessarily the least or the extrema in these. So that's a thing. With the acceptance of the wave theory of light, it was recognized that Fermat's principle applied to geometrical optics and Maupertuis to particle dynamics. So particle-wave duality, and in these days there's consideration of the real wave function, while at the same time that linear frames are free-moving. Vis-a-vis that rotational frames are free-rotating, so there's at least these things. William Rowan Hamilton introduced a characteristic function of optical action, demonstrated a strong analogy between the path of a ray in optically inhomogeneous media and the trajectory of a particle subject to forces. This is the geometric side of it. And so optics is why light is not geometric, while at the same time it kind of follows a line and is geometric in that sense. This is kind of all about it, is the thing. Demonstrate a strong analogy between the path of a ray and a particle. He found a new form of variational principle with the Lagrangian as integral, Hamilton's principle, and introduced a function, now known as the Hamiltonian, whose derivatives give the time rate of change of momentum and position, Hamilton's canonical equations. So in all particle physics and Broncat and all that kind of stuff, it's Hamiltonians. And then also it's Bayesians. So it's as with regards to momentum and whether or not these central principles after Maupertuis, Euler, and Gauss, and Lagrange come as with regards to these Hamiltonians, that these days then when they try to solve things, they basically just kind of apply initial nonlinear contributions to the Hamiltonians. This is with regards to the Bayesians. When really, from the theory underneath, you can kind of get an idea that the partial view is not so necessary from all perspectives, and that statistics and expectations are not necessarily Bayesian. So it takes a pretty thorough account to try and kind of figure this stuff out. Treating momentum mathematically on a par with position made possible the formulation of mechanical problems as the discovery of a function satisfying a set of partial differential equations of the first order. Hamilton's unnecessarily complicated scheme was simplified in 1837 by Jacobi. Let's see here. I'll try to read through this next section. Extensions in mechanics in the 19th century include the profound analysis of vibrations, summarized and completed by Lord Rayleigh, the powerful new hydrodynamics of viscous media pioneered by Nayfeh and Stokes, the theory of elasticity, developed on the basis of distance forces by Nayfeh, Cauchy, and Saint Venant, and the statistical approach to systems of particles introduced by James Clerk Maxwell. These extensions yielded ingredients for other branches of physics, the theory of vibrations for acoustics and electrodynamics, hydrodynamics for the vortex atom, and some representations of the electromagnetic ether, the theory of elastic solids for the undulatory theory of light, and the statistical approach combined with the Hamilton-Jacobi method for statistical mechanics. So statistical mechanics and second thermal law and entropy is given as the law of least action today. It's like, after all this stuff that's kind of already assembled, this is what you get. And so this is what we use to add back up. This is our theory, how everything adds back up. If you want to figure out how it actually works in a dynamical system, you kind of have to tussle it back out through all this stuff. But it just goes to show that statistical mechanics and the statistical ensemble is very much the milieu today to explain how these particles work geometrically in terms of waves in the optical, which they don't. Except ideally. That then there's this further ideal in terms of the real. The great reach of 19th century mechanics and the generalized principle of energy conservation encouraged the hope that all natural phenomena might ultimately be represented in terms of mechanical quantities, mechanical reduction. So it's like our severe abstraction, our mechanical reduction. In our century, however, although it has been applied to important new fields such as aerodynamics, mechanics has lost its preeminence. Firstly, it suffered significant modifications to suit it for describing the behavior of bodies in very rapid relative motion, relativity. Secondly, it was found incapable of fully representing the physical world, quantum. Well, here that's a continuum mechanics again. This last discovery was made with its help. The most penetrating discussion of the nature of the quantum occurred within the framework of statistical mechanics. Hamilton-Jacobi equations supported the old quantum theory and pointed the way to matrix mechanics, while Hamilton's analogy followed beyond the limit of geometrical optics, guided the inventors of wave mechanics. So what this goes to, and this concludes the section, and then we've already kind of read the bibliography of that. And one thing not unmentioned was with regards to the quantum mechanics and the statistical interpretation, more the statistical ensemble, is this with regards to the Bayesian and with regards to the probability theory and the laws of large numbers, plural, that go to show that there's much more to that system of surrounds also that needs to be turned over again, the knockabout, as it were, of these items that so that then can result that there's this fuller dialectic. So what I hope to do today was to talk about momentum and a perceived gaffe with regards to momentum and inertia, because this theory of potentials was the context and not so much, the usual abstract perspective of the setup, but this whole sum of potentials. And with regards to that, I had already been kind of familiar with these developments of these things. I'll be looking again to D'Alembert's principle and Hamilton's principle a little bit with regards to Hooke's law. So, and it's with regards to that Hooke's law is kind of like the one of the first examples of these kinds of mechanical reductions, or in the case of when a severe abstraction is only yet one branch. There are others. They're plural. These singularities or multiplicities. So that's what I hope to do today, and I feel rather gratified that it's so. Space sciences. Randomly selecting a page. Production and removal of electrons in the ionosphere. Energy and ionization. An ion is a charged particle. So particles generally considered here with their position and momentum a function of their mass and velocity, then also with regards to charge. So the field theory and the forces in it all have, there's ideally, you can consider any of these fields on its own when that's the only thing there is to it, like electrical and magnetic and kinetic and the nuclear and radionuclear. And then as with regards to the grand unified theory or unified field theory, how that's all one kind of thing, where a unified field theory is like a branch, and it's not quite a grand unified theory or a theory of everything, that the field theory is a theory of everything. There is a theory of everything already. It's not particularly detailed. It's kind of sensible. What is it? It's a theory, the theory of everything. What's in it is like, it doesn't say, some assembly required and this kind of stuff. So it's like trying to figure that kind of thing out is helpful sometimes. And he talks about recombination. And so the idea of the quantum electrodynamics today is that, is what happens is like our wave collapsed and now we got particles. So we can add them up by these statistics and these classical laws of rectilinear motion. It's like, okay, great. And it's like, what happens when the scattering and tunneling is figured out? So it's kind of like the waves between them, or the continuous manifold. It's like, what you do is imagine all these virtual particles just kind of winking in and out of existence, and so you just make a chain of those like a little net, and then whenever those connect, then you just say that's kind of the thing. You can use vector addition on it and kind of come back and out of it. It's like, well, that's great. these are dynamics that are a little bit less than ideal, yet kind of add up to that. In a different, fuller, wider sense, the continuum mechanics, they are ideal again. So it's this idea that the classical is only the last bit of the real sum of potentials, and then that ideal is only a limited view perspective on. Otherwise, the ideal has that it's still kind of a monistic holism yet, which is nice. A special form of recombination, which apparently occurs to some extent in the ionosphere, is dissociative recombination. An ionized molecule combines with an electron, and as a result, enough energy is released to dissociate the molecule into its constituent atoms. That's the overall reaction. And then they have the attachment process, reflection and absorption. And then he talks about the D region, Lyman alpha, 1216 angstroms. The ionosphere. So that was discussed a little bit more, and it's just kind of close the talk as that it is ideal again. And momentum is a particular perspective. And there are others, it's paleo-classical, and as well paleo-nouveau classical, or since the Renaissance and the Enlightenment age, as well today. And even these days, these things are just being expanded, kind of like so here. Have a great day. Until next time.